So we'll start now. Today, I'm planning to cover two handouts. Okay. Two handouts. The one which I have already sent you, and I have prepared another one also. So today we want to cover both. Okay. So I will be a little fast today. Also, I will avoid writing much on the writing pad. So I will just explain the things on the handouts, okay, because we have to manage the time also. So that is why I'm planning to do so today. Okay, right. So anyway, so just use the whiteboard to give some divide things that we discussed in the last class. Okay, so if you have a function fx, okay, then if you have a function fx, then actually we can, if that function satisfies those three conditions. One is piecewise continuity, absolutely integrable, and right and left hand derivative exist. So we can express fx in the form of Fourier integral representation. How it is equal to uh, 0 to infinity, 0 to infinity, 0 to infinity, a omega cos omega x plus b omega sin omega x into d omega, where a omega is equal to, remember, 1 over 5 integration also minus infinity to plus infinity, minus infinity to plus infinity, f of u, same f of u into cos u omega into d. Similarly, e omega is equal to 1 over 5 into integration minus infinity to plus infinity, f of u into sin omega into sin omega u into d. So these are called the Fourier coefficients. Okay, these are called the Fourier coefficients, and this is called the Fourier integral representation of the function fx. This is called the Fourier integral representation of the function fx. Now, you can use this Fourier integral representation at each point of continuity. At each point of continuity, okay. But at the point of x naught, the function is not continuous. Actually, what you have to do is you have to use this one. X naught plus f of x naught minus divided by 2 a omega into cos omega x naught plus e omega into sin omega. Okay. At the point of continuity, of course, you can use this one. At the point of discontinuity, actually, you have to use this form. Okay. So this is called a Fourier integral representation of the function fx. Okay. Right. Second thing, this is our first thing. The second thing, we studied that if fx is odd function, fx is odd function, then Fourier integral representation. Fourier integral representation will become this way. Fx is equal to integration 0 to infinity. Okay, fx is equal to 0 to infinity. 0 to infinity d omega sine omega. Okay, so we get d omega sine omega x into d omega, where d omega is equal to 2 over 5, 0 to 5 f of u into sine omega u into. So when f is odd, okay, so this is called Fourier sine integral representation. This is called the Fourier sine integral representation. Therefore, if the function is an odd function, okay, Fourier integral representation becomes Fourier sine integral representation. Similarly, third thing, fx is even, then Fourier integral representation. So they write this one. This is called Fourier sine integral. This is called a Fourier sine integral. So that means that fx is E odd, Fourier integral representation becomes Fourier sine integral, because AW becomes 0. Here AW becomes 0. If fx is this one, then AW becomes 0. Therefore, the representation is in this way, and this one we call it as this one. Third thing, if fx is even, then d omega becomes 0. If x is even, then d omega becomes 0. If fx is odd, then a omega becomes 0. Therefore, you can write the Fourier integral representation of fx in this form: 0 to infinity a omega into cos omega x into d omega. Okay. Cos omega x into d omega. Okay, here a omega is equal to, similarly, 2 over 5, 0 to infinity f of u into cos omega u into. Okay, so this is called, actually, so fx is even, then Fourier integral representation becomes Fourier cosine integral. Fourier cosine integral. Okay, so first one is the Fourier integral. If x equal x naught is the point of discontinuity, then you have to take the average of these two. And then if fx is an odd function, then a omega becomes 0. Therefore, Fourier integral representation will have sine component only. Therefore, we say that it's a Fourier sine integral. Therefore, f is odd function. Then Fourier integral representation becomes Fourier sine integral. Similarly, if f is a even function, then b omega becomes 0. Therefore, we have only in our Fourier integral representation, we have only the cos component. Therefore, we say that Fourier cosine integral. Therefore, if fx is a even function, then Fourier integral representation of the even function will become Fourier cosine integral. Okay, so here actually we have seen or we have defined Fourier sine integral and Fourier cosine integral for odd function and even function. But to find the sine integral and cosine integral, Fourier sine integral and cosine integral, function need not to be odd or even. That is the important thing. So that is next note. To find Fourier sine integral or Fourier cosine integral, okay, fx need not to be even, odd or even. Okay, that is we can find Fourier sine integral and Fourier cosine integral for any function when it is defined on half line. Half line means 0 to infinity. Earlier cases, actually, the first one, the range domain is actually minus infinity to plus infinity. So that is the domain. Here also the domain is minus infinity comma plus infinity. Okay. So here also third scenario also the domain is minus infinity plus infinity. Okay. Therefore, first three things are actually Fourier integral representation. Fourier integral representation always we define in the range minus infinity to plus infinity. Okay. If the function is odd function, then the Fourier integral representation becomes Fourier sine integral. The function is even function, then the Fourier integral representation becomes Fourier cosine integral. But we can define Fourier sine integral and cosine integral for any function when the domain of the function is 0 to infinity. When domain of the function is 0 to infinity. And everything is same. So how we are defining? So when the domain is 0 to infinity, okay, fx is a function, okay, the range x is between 0 to infinity, okay, then Fourier sine integral, we define it as fx is equal to 0 to infinity, okay, 0 to infinity, f of x into, sorry, b omega. The same way we got for odd function, b omega into sine omega x into d omega, where b omega is equal to 2 over 5 integration 0 to infinity f of u cos, sorry, not cos, f of u into sine omega u into du. Similarly, you can define Fourier cosine integral, how fx is equal to 0 to infinity a omega cos omega x into d omega, where a omega is equal to 2 over 5, 0 to infinity f of 2 into cos omega 2. Therefore, you have to note this one. To find the Fourier sine integral, cosine integral, fx need not to be odd or even. That is, we can find Fourier sine integral and cosine integral for any function when it is defined on half-line. Okay, when it is defined on half-line. Here the story is different. Here the function is originally defined from minus infinity to plus infinity. Since the function is odd function, the Fourier integral representation becomes Fourier sine integral. When the function is even, here also function is defined minus infinity to plus infinity. Then the Fourier integral representation becomes the Fourier cosine integral. Okay, so this is what we did last time. Also, we had an example. Now, let me recall the example what we did in the last class. I think it is better to do that one again. Okay, here we are asked to find. I remember I gave you an exercise. We are asked to find our fx is given. Our fx is given. Fx is equal to e to the power minus beta x, where beta comma x both are positive. Actually, x is the variable, but now look at here. Actually, the function domain is actually only half line. It is positive. Therefore, we can find Fourier sine representation of this function. Fourier sine representation of this function. Okay, that is the question now. So Fourier sine integral. So Fourier sine integral, we know that to find the Fourier sine integral, actually we want to find b omega. Okay. So before we write the Fourier sine integral, let's find b omega. To find Fourier sine integral, let's find b omega. We don't want a omega. Okay, because we are going to find Fourier sine integral. So b omega is equal to, we know that is equal to 2 over 5 integration 0 to infinity e to the power minus beta u. No, beta u. So we have to replace x by u into sine omega u into du. Actually, now here, if you look at this one, there is a very interesting thing. That is, this is what actually. Can anybody remember? What is this? E to the power minus beta u into sine omega u. What is this actually? So I can directly write the integration of this one. How? Can anybody tell me how can I directly write the integration of this one? Because our course is integral transform. So what is this? Can you identify or can you recognize this integration? So this is what actually. This is what actually. U omega beta. So what is this? Can anybody tell me what is this? 0 to infinity. Look at the limit also. 0 to infinity. What is this? Actually, you don't need to f omega u. No, that's not f omega u. This is not f omega u. This is something else. Because look at the integration. 0 to infinity. What is this section? So this is nothing. No, that's not f beta. No. What is this? This is actually, now if you think u as your t, and omega as your a, and beta as your s. So actually what is this? This is nothing Laplace transform of what? Sine omega u, isn't it? This is nothing Laplace transform of sine omega u. In the place of s, you have beta. In the place of t, you have u. In the place of omega, you have, sorry, in the place of a, you have omega. In the place of s, you have beta. In the place of t, you have the variable u. In the place of a, you have this one. Therefore, this is what actually 2 over 5. And what is the Laplace transform of sine omega u? If the variable is beta, if the secondary variable is beta, this is nothing but omega over beta squared, s squared plus a squared. A over s squared plus a squared, isn't it? A over, what is the Laplace transform of sine 80? Can you remember? What is the Laplace transform of sine 80? A over s squared plus a squared, isn't it? So in the place of s, we have beta. So actually the variable is here t, here u. So we don't need to worry about the variable. In the place of a, we have omega. Therefore, that is omega over beta squared plus omega squared. So you can easily, you can use this. This is allowed. This is allowed. You can use the Laplace transform result to find the integration. Okay, later also we'll do that. Okay, so you can save time. You can directly write. If you just write this, this is same as Laplace transform of sine omega u. You can write this way. If you want, you can write this way. Yeah? This is nothing. The box, the circled one is nothing. Laplace transform of sine omega u, comma, where s becomes beta. That's all. Sine omega u. Actually, this is Laplace transform of sine omega u, where s is here beta. S is here beta. So therefore, you can directly write this one. Now we have found b omega. That is what we want to write the Fourier sine integral. Now we are able to write the Fourier sine integral of fx. So that is fx is equal to integration 0 to infinity. Okay, 0 to infinity. B omega is this one. So we can write it 2 over 5. 2 over 5 omega over beta squared omega squared into sine omega x into. So if you want, you can't take omega out because look at the integration. This is with respect to omega. Therefore, you can't take omega out. Therefore, you can write it as 2 over 5 integration 0 to infinity omega over beta squared plus omega squared into sine omega x into. So this is the Fourier sine integral representation of the function. That. Okay. So that is the answer. I think. Yeah. Look at here. Here they have actually used. Otherwise, you can use if you can't. If this is actually this is what I wrote. This is actually Laplace transform of sine omega u. Omega u. Here variable is t. If you want, you can put t, where s actually is beta. Therefore, you can write the result of that one, and you can easily write this one. Here, actually, they have used integration by parts. Integration by parts to get this answer. But you can later. I thought that so you should recognize these kind of things because actually we are studying this Fourier integral under the same course, no? Integral transform. Therefore, you can use that result, no problem. So wherever you want, actually you can use that result, no problem. Okay. So actually, if you can recognize the variable, then you can use it. Do you understand this, students? Do you understand? Hello, do you understand this one? Tell me whether you understand this. What about others? Okay, fine. Now we are going to move to another thing called complex Fourier transform. Complex Fourier transform. Okay, now only we are going to start Fourier transform. So far, what we have done is we have done three things. One is Fourier integral representation. Then the second thing, Fourier sine integral. The third thing, Fourier cosine integral. Okay, so we know the definition. We know how to find Fourier integral representation for a function, how to find Fourier sine integral representation for a function, and how to find Fourier cosine integral representation for a function. Remember, function need not to be odd or even, need not to be odd or even to find Fourier sine integral as well as Fourier cosine integral. Okay, so we can find Fourier sine integral and cosine integral for any function. If the function is odd function, so when the domain is 0 to infinity, when the domain is 0 to infinity, so here actually the domain is minus infinity, less than x, less than plus infinity. Okay, here both cases the domain is 0 less than infinity, 0x less than infinity. Okay, the function is odd function. Okay, fx is odd function. The Fourier integral representation automatically becomes Fourier sine integral. If fx is even, okay, the Fourier integral representation automatically becomes Fourier cosine integral. Therefore, the even. Okay, so this is the big picture of what we study. This is the big picture of what we study. Okay, normally here, when the domain is 0 to infinity, we can find Fourier sine integral and cosine integral for any functions. Okay, right. Now we are going to define Fourier complex transform. Now only we are going to define Fourier transform. So that we call it as the Fourier complex transform. Fourier transform. Sometimes we can say Fourier or complex Fourier transform. Complex Fourier transform or Fourier complex transform. Earlier one was Fourier integral. Now only we are going to define the transformation. Now look at how we are defining the Fourier integral transform. Now actually we are defining Fourier integral Fourier transform. We are defining complex Fourier transform. Okay, if somebody say Fourier transform, same. If somebody say complex Fourier transform, all are same. Both are same. Or if somebody says Fourier complex transform, both are same. All are same. Now actually we are defining Fourier transform from Fourier integral representation. Okay, now we know that if you have a function fx, then its Fourier integral representation is of the form 0 to infinity, okay, a omega cos omega x plus b omega sin omega x into d omega. Now what I am going to do is, this a omega and b omega, we know that they are Fourier coefficients. Now I am going to plug them here. Okay, so now I'm going to bring the I'm going to replace a omega and b omega by those things. Then this formula will become, this integral representation will become 0 to infinity. In the place of a omega, I am going to put the thing that is 1 over 5 integration fu. Okay, here minus infinity to plus infinity. Okay, minus infinity to plus infinity. Then cos omega u du. Look at carefully what I am doing. I am replacing a omega by its value, that is 1 over 5 minus infinity to plus infinity fu cos omega u. Here I have cos omega x. I am writing that one, cos omega x, plus similarly I am going to replace d omega by its formula, that is 1 over 5. Okay, 1 over 5 integration minus infinity to plus infinity. Okay, f of u sin omega u du into sin omega x. Okay, the whole thing into d omega. Now I'm going to multiply this because I can take because this is independent of u, no, so I can bring inside this one. I can bring inside this one, and I can take 1 over 5 out, and I can write the same in this way. That is, I can write it as 1 over 5 integration 0 to infinity. Look at here, integration minus infinity to plus infinity, minus infinity to plus infinity. I can take fu common. I can write this way, fu. Okay, fu, and this one cos omega u cos omega x. So here, look at here, fu cos omega u, yeah, cos omega x, plus sin omega u sin omega x into, I have two actually, this one is du and this one is d omega. So I can write this as, order is important. The first one should be omega, and then second one, sorry, first one should be du and other one should be omega. So I can write it as du into d omega. Now, if you look at this part, can you remember some formula? Cos omega u cos omega x, cos A cos B, sin A sin B. So what is that? Cos A cos B, sin A sin B. So you can write this as 1 over 5 integration 0 to infinity. Okay, 0 to infinity minus infinity to plus infinity, minus infinity to plus infinity. Okay, minus infinity to plus infinity f of u. Can anybody tell me what is this? Cos omega u cos omega, using the trigonometric formula. Can you tell me what is this? Cos omega u cos omega x plus sin omega u sin omega x. Can anybody tell me what is this? Into, finally I can write this du into d omega. Can anybody tell me what should be here? Yeah, you can write it as cos u minus x omega. Omega is also there, no? It's a constant. So you can write it as cos u minus x omega. U minus x omega. Okay, u minus x omega. Now, keeping this with me, okay, keeping this with me, I'm going to change the order of the init. Order means actually, look at here. I'm writing this way. This is equal to, this is equal to f of u cos omega u x, this one, right? Look at the notes now. So that is what we are doing here. So we are at this point now. Right. Sorry, we are now at this point. I'm sorry. If you want, right? Okay, let me say we are now here. So once you substitute this one, you can get this one. So we are getting this one. I'll explain the next steps. Okay. So now we are here. Actually, here we have the same thing. Look at here. We have 1 over 5, 0 to infinity, minus infinity to plus infinity, f of u cos u minus x omega du d omega. The same thing we are having here. 1 over 5, 0 to infinity, minus infinity to plus infinity, f of u cos omega u minus x du d omega. Now, what you can do is, actually here, you can change the order of integration. Actually here, this limit minus infinity to plus infinity for u, isn't it? 0 to infinity for omega. Okay, now what I am doing is, I am changing the integration. I am writing this one first. Say for an example, if you have two integration, okay, two integration, okay, this one is this one is a to b and c to d, okay, function into say dx into dy. Okay, dx into dy means c to d. Actually, this is the first one. This is the first one. Okay, so this is the first one. Then you have to put this one. So what you can do is, you can change the order of integration. So you can write this as c to d, a to b. There's no change in the function. But again, since you have changed this one, you have to change the order of integration. Then this becomes dy into dx. So similarly, what we are doing here is, we are doing the same here. Okay, we are doing the same here. What we are doing, we are changing the order of integration. So once you change the order of integration, okay, now look at here, this one does not have, actually, this integration is with respect to omega. Therefore, I can take u out. So then I am writing in this way. So do you understand this step, students? Do you understand this step? From this one, how it came, do you understand? I'm changing the order of integration. I'm changing the order of integration. So I think I remember we studied these things in Laplace transform also. Do you understand this step, how this came here? Do you understand how this came here? How this one came here? I'm just changing the order of integration. I'm just changing the order of integration. Now look at here. 1 over 5. 1 over 5. Yeah. I'm changing the order of integration, and then I'm getting this one. Now what I'm doing is, look at here. The next thing is that, what can you say about the cos function? If you have a function like this, minus infinity to plus infinity, if fx is an even function, then you can write this as 2 times integration 0 to infinity fx into dx. Isn't it? So now I am writing the reverse of that one. So if you have some integration like this, 0 to infinity fx dx, if fx is even function, if fx is even function, here if fx is even function, you can write it as half times integration minus infinity to plus infinity. isn't it? So here we know that this cos function is an even function, isn't it? This is an even function. Cos is an even function. Therefore, how can I change this integration 0 to infinity? I can change it as half times minus infinity to plus infinity cos u omega u minus x. Do you understand how this came from this line? Tell me how this came from this line. Actually, since cos is an even function, we are changing the limit of the integration from minus infinity to plus infinity. Because of that, I am putting half here. Do you understand this one? How this came from here? Tell me whether you understand how this came from this step. Hello? Do you understand how this one came? This one came from the previous one. Since fx is an even function, you can change the limit of the integration. You can change it as minus infinity plus infinity. Because of that, you have to put half. Actually, here, if fx is an even function, then minus infinity to plus infinity fx, you can put it as 2 times 0 to infinity fx. You can half the limit. You can half the limit and you can put this way. Okay, so you can do the reverse. You can do the reverse also. That means that if you have a function from 0 to infinity fx, if fx is an even function, then you can change the limit from minus infinity to plus infinity by putting half here. So we are writing in that way. Now look at the limit. Both are minus infinity to plus infinity. This is also minus infinity to plus infinity. Now I am taking this half also out. Then I am getting 1 over 2 pi into minus infinity plus infinity, minus infinity plus infinity, f of u. Now I am bringing this to, bringing this f side inside this one, f of u cos omega u d omega u into this one. So do you understand this, how this came? So this is nothing, just rearranging the terms and we are getting this one. Okay. So now, where are we now is, actually we have written the Fourier integral representation in this form, equal to 1 over 2 pi minus infinity to plus infinity, another integration minus infinity to plus infinity, okay, f of u cos omega u minus x into d omega d. Okay, so this is nothing, another form of Fourier integral representation of the function. Okay, Fourier integral representation of the function. Now I am asking a simple question. If you understand, can you tell me? Okay, can anybody tell me what is the integration minus infinity to plus infinity, minus infinity to plus infinity, sine omega u minus x into dx, d omega. Can anybody tell me? Sorry, d, yeah, omega sine omega u minus, what is this? What is the value of this function? Can anybody tell me? Sine omega u minus x into d omega. Can anybody tell me what is the answer of this one? I'm waiting for your response. What is the answer? Without calculating, you can be able to tell this one. Yesterday we studied, last class we studied. Now, this is a sine function. This is a sine function. This is like a constant because we are integrating with respect to omega. So this is what function? This is an odd function. Okay, so can you remember minus L to plus L fx dx equal to what? Equal to what? Can anybody tell me? Fx is odd function. If fx is odd, can anybody tell me? Fx is odd. What can you say about this one? Sine omega minus u dw. Yeah, that is 0. That is 0. So sine is an odd function. Therefore, look at here. It's an odd function. Can I show you that? Here. Look at here. The function is the odd function. Then minus L to L fx dx is equal to 0. Isn't it? Minus L f of x dx is equal to 0. So I am applying the same thing. Therefore, minus infinity to plus infinity sine omega ux dw is equal to 0. Therefore, from this one, I am going to multiply by a constant I. I is a complex number, imaginary part, that is I equal to here square root of minus 1. Because I am going to now express the function in terms of complex Fourier integral. Okay, that is why I am introducing I. So I into 2 pi integration minus infinity to plus infinity omega sine omega u minus x d omega equal to 0, where I equal to square root of minus 1. Because this is already 0. We know that this one is 0. We know that this part is 0. Okay, we know that this part is 0. Since this part is 0, by multiplying I over 2 pi will make no change. Therefore, I over this one is 0. Okay, therefore, I can still write this as, I can write this, look at here, how we are writing that. Look at here, minus infinity to plus infinity, sine omega x, sine omega u minus x is equal to 0, because the reason is sine omega u minus x is odd function. Therefore, what you can do, you can say that integration, because this part is 0, no? This part is 0. Therefore, from this one, what you can say? Even you can say I over 2 pi integration minus infinity to plus infinity f of u integration minus infinity to plus infinity sine omega u minus x into d omega equal to 0, because this part is 0 again. This part is 0, no? So this part is 0. Therefore, you can write this one. From this one, you can write like earlier one. That is I over 2 pi minus infinity to plus infinity. Minus infinity to plus infinity. F of u into sine omega u minus x into d omega. Sorry, here du is missing. Sorry. Du equals. So this is somewhat similar to what we have here. So earlier one, we have what we are having 1 over 2 pi minus infinity to plus infinity minus infinity to plus infinity f of u cos omega u minus x into du d omega. Now we have shown that I over 2 pi minus infinity to plus infinity minus infinity to plus infinity f of u sine omega u minus x d omega du is equal to 0. Therefore, now I am going to add these two. This is my first one. This is my second one. Now, if I add 1 plus 2, what I can have here, actually this part I have added this. Fx is actually this one. This is correct. But this is 0. Therefore, we are just adding that one. Actually, this is the original one. With that one, since this part is 0, I am adding this one. So this is 0. Therefore, it will make no any effect to that one. So now what I have is actually here. Look at here. Now I have is f of u and I have cos omega. Now I am taking 1 over 2 pi out. Now I am taking 1 over 2 pi out. Look at here. I am taking 1 over 2 pi out. Now what I have is minus infinity plus infinity, minus infinity plus infinity, f of u. Even if I take f of u common, what I have is cos omega u minus x plus I into sine omega u minus x into d omega into. This is what actually. This is what actually. So can you remember e to the power I theta equal to what? E to the power I theta equal to what? We know that cos theta plus I sin theta. Isn't it? So cos theta plus I sin theta can be written as e to the power I theta. So what we are having here, cos omega u minus x plus I times sin omega u minus x. Therefore, you can write this as e to the power I omega u minus x. I omega u minus x. Okay, so this is actually 0. This is actually 0, but we are adding in order to express our integral in the form of complex number, in the form of complex integral, in the form of complex integral. Just by adding this one, what you can do, you can use the this idea. You can use this e to the power I theta equal cos theta plus I sin theta, and you can write this one. Instead of cos omega u minus x plus I sin omega u minus x, you can write e to the power I theta. Instead of theta, what you have? Omega u minus x. So omega u minus x. So now fx you have written in terms of this one. So this is called, okay, Fourier complex integral of fx. Fourier complex integral of fx. Here no coefficients. We have put all the coefficient in the formula, in the expression, and we have got the final formula. Therefore, this one is called fx equal, okay, fx equal 1 over 2 pi, okay, 1 over 2 pi, okay, integration minus infinity to plus infinity, minus infinity to plus infinity, f of u e to the power I omega u minus x into d omega d u. We call it as complex Fourier complex integral. We call this as the Fourier complex integral. So actually we have derived this from Fourier integral representation. From the Fourier integral representation, our starting integral representation, we have derived this one. We have used some techniques here. We just added this part. We added this part because that is 0. And we are using this idea e to the power I theta equal cos theta plus I sin theta formula. And we are putting that and we are getting this one. Do you understand this, students? Do you understand this one? Do you understand this one? Okay, fine. What about others? Only 272. What about others? I will understand. I get only few responses. I don't know whether others understand or not. Right. So this one we call it as the Fourier complex integral of fx. This one we call it as the Fourier complex integral of this one. Now look at here. Now I'm going to rewrite this one. So now we have the Fourier complex integral. So we have Fourier. Look at this carefully. Now I'm going to introduce another thing. Fourier complex integral of the function fx. We write it as fx is equal to 1 over 2 pi, okay, integration minus infinity to plus infinity, okay, integration minus infinity to plus infinity, f of u, look at this carefully, f of u into e to the power I times, okay, omega u minus x into d omega d omega du, d omega du. Okay, now look at here. I'm just going to write this in another form, 1 over 2 pi integration minus infinity to plus infinity. Okay, I'm changing the color for some purpose. Then I'm writing minus infinity to plus infinity f of u minus infinity to plus infinity f of u. This one I'm using the laws of indices. I can write it as e to the power I omega u, okay, I omega u into d omega, I omega u into I omega u into, because I'm changing the order. I'm changing the order of this integration. Look at here. I omega u into d omega, because here I don't want to change this one because both are minus infinity to plus infinity. Therefore, d omega first, du first. So du, okay, du. Then what I'm doing is, okay, let me put a bracket here. Bracket into, okay, I have balance e to the power I omega minus x. So I can write it as e to the power, so minus I omega x into d omega. Okay, I can write this. I can just split this one. E to the power I omega u minus x. I can write it as e to the power I omega u into e to the power minus I omega x. Okay, now look at here. The red color one. The red color one, we call it as Fourier transform, Fourier complex transform, Fourier transform of the function fu. So we call this red color one as this one, red color one as Fourier Fourier complex transform. Or you can say just transform, Fourier transform. Fourier complex transform of fx. So look at here. This part we call it as the Fourier complex transform, and we write this way. Here we are using f. In Laplace transform we use capital L, isn't it? Here we are using f, script f, not just f. The Fourier transform of fx is equal to, okay, here actually our variable is what? We are integrating with respect to u. Here our secondary variable is omega. Therefore, the answer will be in omega. Therefore, Fourier transform of fx will be equal to f bar. We are using the transformation as f omega equal to integration minus infinity plus infinity f of u e to the power, okay, I u omega into. This is the definition of Fourier transform or Fourier complex transform of the function fx. Okay, so this is the definition of Fourier complex transform of the function fx. And here in Laplace transform, what we are doing? Our function is capital Ft, and the transform function is fs. Similarly, definition is what? 0 to infinity e to the power minus st into capital Ft. Similarly, here our function is fx. Our function is fx. The transform function here, the secondary variable is omega. Therefore, here we are denoting by, here we are using one for capital and other for simple. Here we are using both capital. In order to differentiate, we are using a bar. We are using a bar. So this is our transform one, and this is our definition. So here the kernel is e to the power I omega, sorry, e to the power I u omega. So this is the kernel. Here this is the kernel. This is the kernel. Here this is the kernel. Therefore, this is the definition of Fourier transform of a function fx. Okay. So here we are getting the Fourier Laplace transform in S. Here we are getting the Fourier transform in omega. Here we are getting the Fourier transform in omega. Okay. So that is the definition. Do you understand this definition, students? Do you understand this definition? Hello, do you understand this definition? Right. Now, having understood this one, now what I am going to do is, now I'm in this Fourier integral representation, I'm going to replace here by Fourier transform. Therefore, we have the Fourier integral representation is 1 over 2 pi integration minus infinity to plus infinity. Okay, integration minus infinity to plus infinity f of u e to the power I omega u d omega. Okay, into e to the power minus I omega x into d omega. We are saying that this is our Fourier transform of the function. Therefore, I can write this as 1 over 2 pi integration minus infinity to plus infinity. This is nothing Fourier integral of fx. Therefore, I am writing Fourier integral of fx into, okay, e to the power. So let me write that one using e to the power minus I u, sorry, I omega x into d omega. Okay, so the transformation, Fourier transformation, Fourier integral can be write in this way. Therefore, now this is our fx. Therefore, if so, what is this actually? This is the definition of Fourier integral. Fourier integral. Now, you know that. So, if you want, you can write this as. If you want, you can write this as 1 over 2 pi integration minus infinity to plus infinity. This is nothing. You can write it as f bar omega e to the power minus I omega x into e minus I. So now look at here. So when you take this one, f bar omega e to the power I minus x, it gives fx. It gives fx. So what is this actually? Can anybody tell me what is this? Now, if you remember, if Laplace transform of, look at here, if Laplace transform of ft equal to fs, okay, if Laplace transform of ft equal to fs, then the inverse Laplace transform of fs is equal to what? Can anybody tell me? Inverse Laplace transform of fs is equal to what? Inverse Laplace transform of fs is equal to what? Can anybody tell me? What is the inverse Laplace transform of fs? If Laplace transform of ft equal to fs, what is the inverse Laplace transform of fs? Can anybody tell me what is the inverse Laplace transform of fs? Just tell me the definition. If Laplace transform of ft equal to fs, what is the inverse Laplace transform of fs? I'm waiting for your response. Please. What is the answer? Yes. So that is nothing but ft. So ft is actually inverse Laplace transform of this one. Therefore, here, what is the, here fx is what? So inverse Fourier transform of f bar omega equal to f omega fx, isn't it? So Laplace transform of ft equal to fs. Then inverse Laplace transform of fs is equal to ft. Similarly, inverse Fourier transform of f bar omega should be fx. So, but this is equal to what? According to this formula, 1 over 2 pi integration minus infinity to plus infinity f bar omega into e to the power minus I omega x. Okay, therefore, the inverse Laplace transform of, the inverse Fourier transform of function is given by this formula from this part. Because look at here. So I'm writing it again here. The Fourier transform of a function fx is equal to, we denote it by f bar omega, is given by integration minus infinity to plus infinity f of u e to the power I omega u. This is the Fourier transform. Inverse Fourier transform. This is Fourier transform. Inverse Fourier transform is f inverse of this function f bar omega is given by, okay, Look at the formula. 1 over 2 pi is equal to fx will be equal to 1 over 2 pi integration minus infinity to plus infinity. Okay. The Fourier transform of the function f omega e to the power minus I u minus I omega x into. Okay, so don't get confused. Look at here. Here plus I omega u du. Here minus infinity to plus infinity f bar omega into e to the power minus I omega x into d omega. Okay, that is d omega, not dx. Do you understand how to find the Fourier transform? And so actually we have derived, or we are defining Fourier transform of a function and its inverse transform from the Fourier integral. We are deriving these two formula, that is Fourier transform and Fourier integral transform, Fourier transform as well as inverse Fourier transform using Fourier integral representation of a function fx. Okay, so that is the definition. Do you understand up to now, students? Do you understand up to now? So you have to by heart these two formula: how to find a Fourier transform of a function and how to find the inverse. So both are integration. So if you want to find the Fourier transform, minus infinity to plus infinity fu e to the power I omega u into du. Okay. If you want to find the inverse of that one, remember there is 1 over 2 pi. There is 1 over 2 pi minus infinity to plus infinity f bar omega. That means the Fourier transform of the function fu into e to the power minus I omega x. So look at here. Two integrations are there. So you have to clearly remember to find the Fourier transform, which variable we have to integrate with respect to. To find the inverse Fourier transform, which variable we have to integrate with respect to. Look at here, there is a coefficient 1 over 2 pi here. There is no coefficient 1 over 2 pi here. Okay, so you have to remember all these things. Okay, so these are the two definitions. These are the two definitions. And this is called, this one we call it as the Fourier, this one. This one we call it as the Fourier complex integral. This one we call it as the Fourier complex integral. Okay, from the Fourier complex integral, okay, we are defining two things. We are splitting this into two parts, and we are taking this, we are defining this as the Fourier transform of the function, and using the same idea, okay, we are defining the inverse Fourier transform. Do you understand, students? Hello, do you understand this one? Tell me whether you understand this or not. Do you understand up to now? Right, fine. Now let's have some example. So everything is mentioned here. So the same thing. Okay, now we'll find the find the Fourier transform. Fourier transform of the function fx equal to 1 minus x squared, this one. And hence evaluate x cos x minus sin x x cube and this one. Okay, now let's find out this value. Right. So the function is 1 minus x squared. So look at here. The function is given like two-way 1 minus x squared when mod of x less than a 1, here 0 if mod of x is greater than 1. So mod of x less than 1 means minus 1 less than x less than 1. This one is actually you know that one, otherwise 0. So now we are going to find the Fourier transform of this function fx. Okay, Fourier transform. This is script f. Script f. We call this as script f. Okay, this is called the script f. So not just f, we are putting that one. Okay. So Fourier transform of fx. Now we are going to find this one. We are going to use the definition to find this one. So this is equal to, okay, this is equal to, we know that integration minus infinity to plus infinity f of u. Okay, this is the definition. We'll try the definition first. F of u into e to the power I omega u into d. So that is the definition. Look at here, there is no minus. Inverse only we have minus. So now, if you look at the function, -1 to +1 only function is 1 minus x squared. Otherwise, function is 0. Therefore, it is enough to consider that range only, -1 to +1. We have to put fu. So function is given in x. We have to change the variable. So we can put it as 1 minus u squared. 1 minus u squared e to the power I omega u into. We don't need to consider other range because in other range function is 0. Now, if you integrate using integration by parts, okay, using integration by parts, let's keep this function as it is, 1 minus u squared, 1 minus u squared into, if you integrate this one, e to the power I omega u over I omega. No? So we have to put the limit -1 to +1. -1 to +1 minus integration, differentiation of this one. So that is -2u into integration of this one, which is equal to e to the power I omega u over I omega into e. But actually, if you put +1, this becomes 0. Even if you put -1, this part becomes 0, isn't it? Here, if you substitute I equal +1, 1 minus u squared is 0. Even if you put -1 here, this part 0. And here, we get a -2 over I omega out. You can take this part out. You can take u out, but you can take omega out. So you can write it as minus into minus plus. It becomes 2 over I omega. 2 over I omega integration u into e to the power I omega u into -1 to +1. Here also -1 to +1. Now I am going to integrate it again. So 2 over I omega. Now if you integrate this one, u into e to the power I omega u over I omega, because I am integrating with respect to u. So e to the power I omega u over I omega minus, and if I integrate this one with respect to u, I will get 1. Therefore, I will get integration -1 to +1. -1 to +1. If I differentiate this one, that is 1. Therefore, I can write e to the power I omega u into du. Here I want to substitute the value -1 to +1. Now, again, if I do this one, I can have 2 I omega. And here, okay, I'll keep that again. So here, we'll keep that u into I omega u over I omega. I want to substitute -1 to +1 minus, if I integrate this one, I will get e to the power I omega over I omega. Again, I want to substitute +1 to -1. I omega u, no? Now I can bring all I omega here. I can bring all I omega here, and then I can write it as 2 over I squared omega squared. And here I have u into e to the power I omega u minus e into I omega e into I omega u minus 1 to plus 1. I don't know whether I'm making any mistake here. So if I put plus 1, so 2 over I squared omega squared into, if I put plus 1, then I will get e to the power I omega, okay, e to the power I omega minus e to the power I omega, okay, that vanishes. And if I put okay, you keep that minus, and if I put minus 1, sorry, I don't know whether, am I correct or wrong? Yeah. So if I put minus 1, then I'm getting minus e to the power I omega minus I omega, e to the power minus I omega. Here if I put plus 1, that is okay. Here I get e to the power minus I omega minus e to the power minus e to the power minus I omega. So this becomes 0, and if I take minus out, so that becomes 0. So I get here 2 over I squared omega squared into how can I write this one? Okay, I don't know whether I'm correct here. Minus out, so I can write it as let's check the answers. Okay. Okay, here this part becomes 0. That's true. And then if you integrate this one, we are getting that, no? Omega u into u into I omega. I omega already we have got out. Sorry, I omega we have got out. E to the power omega minus this one. So please check these answers. Okay, I'm sorry, we don't have time, so that's why. Anyway, this part is 0. Therefore, you can take this out. This is actually equal to 2 times 2 over I omega integration minus 1 to plus 1. Okay, u into e to the power I omega u into d. Then 2 over I omega is out. Again, you are integrating. So u into e to the power I omega u over I omega, that is correct. So this is correct. And this is minus 1 to infinity. And if you integrate this one, that is 1 into e to the power I omega. So that is correct. Then again, I squared is equal to minus 1. We know that I squared is equal to minus 1. No? So I'm putting that I squared is equal to minus 1. So 2 omega squared e to the power I omega plus. So once you substitute the value, you will get this one. Okay, that's all. So e to the power, I'm sorry for that. So you can put e to the power I omega plus e to the power minus I omega and this one. Okay. Now we know that e to the power I omega equal to, we know that cos omega plus I sin omega, isn't it? I sin omega. E to the power minus I omega, we know that that is equal to cos omega plus I minus sine omega. So you can write it as minus I sine omega. Okay. So if you add these two, e to the power I omega plus e to the power minus I omega, that becomes 2 times cos omega. So that is why we are putting for this one, we are putting 2 times cos omega. And here, once you substitute this one, so actually this one, if you subtract this one, 1 from 1, e to the power I omega minus e to the power minus I omega, that becomes 2I sine omega. So that is why we are putting 2I sine omega, but already we have I here. Therefore, when it is divided by that one, so e to the power I omega over I, so that is equal to 2 sine omega. So we are putting this one. So finally, the Fourier transform of the given function becomes this way. So this is the Fourier transform of the function. Do you understand up to now, students? Do you understand? This is just integration, A level. This is just integration. We are using the definition and we are evaluating. Here, you have to use this one. E to the power I omega equal to cos omega plus sin I omega. E to the power minus I omega equal to cos omega minus sin I omega. So if you add these two, you will get 2 cos omega. And if you subtract second one from first one, you will get 2I sin omega. When you divide by I, you will get 2 sin omega. So I'm just replacing that one and taking this omega out. So when I take omega out, so it will be multiplied this one and I getting this one. Do you understand this one, students? Do you understand or not? Tell me whether you understand or not. Right. So now what we have is we have found that the Fourier integral of fx is equal to f bar omega equal to minus 4 times, I can't remember, minus 4 times omega cos omega minus sin omega over omega q. So this is the answer. This is the Fourier transform of the function. Okay, this is the Fourier transform of the function. Now there is one more question. Look at the question here. So first one, they are asking you to find the Fourier transform of the function. Then they are asking you to evaluate this one. Hence, evaluate 0 to infinity this one. Okay. So, so how to evaluate this one? That is the question now. Look at now. So to evaluate this one, actually, we are going to use the inverse Fourier transform. Inverse Fourier transform. Why? Because we are getting something similar to this one. We are getting something similar to that one. Minus 4. Look at here. Omega cos omega sin omega over omega cube. So we are having something. So definition, according to the definition, fx is equal to, I'm writing the Fourier transform. Inverse Fourier transform. The inverse Fourier transform of f bar omega, according to the definition, is fx, which is equal to 1 over 2 pi integration minus infinity to plus infinity. Minus infinity to plus infinity. Okay. So what is the Fourier transform? Actually, definition is what? What is the definition of this one? 1 over 2 pi integration minus infinity to plus infinity f bar omega e to the power minus, remember minus is there, minus I omega x into d omega. Remember, that is the formula. So now I am using that one. 1 over 2 pi. Already we have found this one. This is the Fourier f bar omega. So I am going to put that one. So minus 4 omega cos omega minus sin omega over omega cube into e to the power minus I omega x, okay, into d omega. Now what I am going to do is, for this one, I omega x e to the power minus I omega x, according to the definition, I can put this one, cos omega x minus I sin omega x, isn't it? E to the power I omega x is equal to, this is my theta, I omega x into, okay, cos omega x minus I sin omega x. Now what I am going to do is I am going to replace this sin I omega x by this one, and I am going to equate the real part, because if you look at the function fx is actually a real valued function. It's a real valued function, so there is no any I. Therefore I don't want to multiply by this I actually. So this one you can write it as, okay, 1 over 2 pi. You can say that fx is equal to, you can say that fx is equal to 1 over 2 pi minus plus infinity, okay, minus 4 times, okay, so I'm taking this minus 4 also out. So I'm taking this minus 4 also out. So if I take minus 4 also out, then I have minus 4 here, minus 4. Then cos omega, look at here. What I have is omega cos omega minus sin omega divided by omega cube. And now I am not going to multiply by this part, okay, or multiplying by this part, but I am taking only the real thing, because fx is a real valued function. So into, I have cos omega x, isn't it? I have cos omega x, cos omega x. Therefore now if you look at the thing we want, look at the thing, look at now, actually we don't have omega, we have x only. Here we have is fx is equal to, actually we have fx is equal to integration minus 4 over 2 pi, minus 4 over 2 pi. Here it is minus infinity to plus infinity, omega cos omega minus sin omega over omega cube into cos omega x into d omega. This is what I have actually. So what is the suitable value I can put? Look at the limit also. Limit is 0 to infinity. Limit is 0 to infinity. So now if you look at this function, okay, if you look at this function, this function is actually an even function. This function, the entire function is even function. You can check that one. How you can check that one? If you put x equal minus x, okay, minus x cos minus x minus sin minus x, okay, over minus x whole in cube into cos minus x by 2. And if you simplify this one, you will get minus x cos x, minus into minus is plus sin x, over minus x cube. Here cos minus x by 2 is same as cos x by 2. Okay, now if you multiply by minus up and down, you will get the same function. Therefore this function is an even function. So since it's an even function, you can break the limit 2 times 0 to infinity. Okay, so you can break the limit as 0 to infinity. Look at here. Yeah, we are getting this one, and here we are multiplying. So this one is replaced by cos omega x minus I sin omega x. Actually, I have 1 over 2 pi. I have 1 over 2 pi. The limit is minus this one. I'm taking minus 4 also out. So minus 4 also out. So then I can write it as minus pi by 2 because I'm taking the whole thing there at the side. So minus pi by 2 fx. Minus pi by 2 fx. Now what I'm doing is I'm writing this. I'm equating the real part. I'm equating the real part. So if I equate the real part, I will get omega cos omega minus sine omega or omega cube into cos omega x is equal to minus pi by 2 fx. Minus pi by 2. Actually, this is coming from the inverse Fourier transform. Inverse Fourier transform. I'm putting the inverse Fourier transform. I'm taking minus 4 out. Then I'm writing this way. Now we know that. So for what value of x? For what value of x, you will get this integration. For what value of x, you will get this integration. Look at x cos x, sin x, x cube, x by 2. So we are having a similar thing here. We are having a similar thing here. Look at here. We are saying a similar thing here. Here our variable is omega. Here our variable is omega. We have, in addition, we have x also. So what is the possible value for x so that you can get that part? What is the possible value for x? What is the suitable value for x so that you will get the exact integration like x cos x minus sin x? Look at here. If you put x equal half here, look at here. If you put x equal half here, what you will get? Minus infinity to plus infinity omega cos omega minus sin omega by omega cube into cos omega by 2. If you put x equal half, we are getting the same one. Here the variable is omega. There in the integration, the variable is x. Don't get confused. Equal to actually minus pi by 2 into x equal half is a continuous point. Look at here. X equal half is a continuous point. Therefore, we can put the exact value of x. Half. So half mean what? F of half is what actually? F of half is 1 minus 1 over 2 square. So which is equal to 3 by 8, isn't it? Which is equal to 3 by 8. So I am putting 3 by 8. Also look at the integration. Integration is what? 0 to infinity. But this is an even function. Therefore, what can you do now? What can you do? So you can change the integration as 0 to infinity 2 times. Then you can get the answer as 0 to infinity. Here variable is omega. I'm changing the variable as x again, and then I'm getting the answer minus 3 pi by 60. So using this one, we can get this answer. Do you understand this one, students? I know it's difficult, not very difficult, but you have to follow the rules. You have to, if you use the definition, you can get the answer. So actually, there is a confusion here. That is the variable confusion here. Now you must know that this function is an even function. This function is an even function. Okay, so that is why we are changing the limit. So actually, you have to think from the answer. You have to think from the answer. You have to think from what is asked here. They are asking the integration 0 to infinity. Okay, now say for an example, if you want to find the integration of this one, say if you want to find, look at here, I'll tell you one more thing. Now, if you want to find the integration, this one, 0 to infinity, x cos x minus sin x over x cube into cos x, then what will be the answer? Can anybody tell me? Here, actually, we want to find the integration 0 to infinity x cos x minus sin x divided by x cube into cos x by 2. Okay, and we got the answer that minus 3 over 16/5, isn't it? That's the answer. Yeah, 3/5 over 60. That is the answer. Now I'm asking if they ask this one, cos x What will be the answer? Look at here. Look at here. Now we just substituted this value in the function because at x equal half the function is continuous. But if you look at the original function, when x equal 1 the function is not continuous. When x equal 1 function is not continuous, isn't it? Because at that point the function is 1 minus x squared, so that is broken. Okay, so here it is discontinuous. X equal 1 function is discontinuous. Therefore, actually here what you have to put is here. Look at here. Here actually what you have to put is, okay, here what you have to put is, you have to put for this one, okay, for this one, sorry, for this one you have to put, for this one actually you have to put f of 1 plus f of 1 minus divided by 2. Okay, f of 1 minus f of 1 plus f of 1 minus f of 1 plus divided by 2. Because if x equal 1, because here look at here we are asked to find x, therefore our omega should be, sorry, our x should be what here. To compare this one, to compare with that one, you have to compare with that one here. So you have to put x equal 1. Here it was, since it was x by 2 only, we put this one. Okay, since it was that only, we put that one. Okay, right. So I think you understand this one. Do you understand this one, students? Tell me whether you understood this one. Okay, actually you have to do a lot of work here. First thing, that is, now if you have a confusion here, if you have a confusion in x and something, okay, better what I am doing is, what I tell is, you just think like this. You just change this x by this way. Find 0 to infinity lambda cos lambda minus sin lambda over lambda cube into cos lambda by 2, because we are having a x in our question, no? Therefore sometimes you may have a confusion. So if you have a confusion, please change this x as lambda. Please change this x as lambda, then you will get rid of some confusion. Okay, now I'm just explaining it again quickly. First, we are finding the Fourier transform of this function. So then Fourier transform of this function, we get like this one. Using this one, actually we want to evaluate this integration. Evaluate this integration. Now to evaluate this integration, actually what we have to do is, we have to consider inverse Fourier transform. So inverse Fourier transform. According to the definition of inverse Fourier transform, we have 1 over 2 pi minus infinity to plus infinity f bar omega e to the power minus I omega x into d omega. Look at minus is there. Now what I am doing, I am just replacing f bar omega by what we found in the previous step. That is, we are replacing this by Fourier transform of the given function fx. Okay, then it is there. Then what I am doing is, now look at, this is a constant, I can take it out. So if I take it out, that will become minus 2 over pi. So I'm just having a cross multiplication, minus 2 over pi. So right hand side or left hand side, that will become minus pi by 2 fx. Now I am replacing this e to the power I omega x by the well-known formula cos omega x minus I sin omega x. Now if you look at this part, right hand side, this is a real function. Therefore, I consider only real part of this integration. I consider only the real part of this integration because my function is a real valued function. My function is a real valued function. Therefore, I consider only this part of integration. Then I get this one. Okay, I get this one here. Then what is happening here? Actually, if you compare with this one, if you compare this one, okay, what is the suitable value I want to put? Lambda cos lambda sin lambda cos lambda by 2. So what is the suitable value I want to put here? X equal half. Then I will get omega cos omega. That means that lambda sin lambda cos lambda minus sin lambda divided by lambda cube cos lambda. If I put x equal half, I will get cos lambda by 2. Therefore, I am choosing x equal half. Therefore, right hand side also I want to put x equal half. So if I put x equal half, then I'm getting 1 minus 1 over 4 because my function is 1 minus u square. Now, if this was lambda, what is the suitable value I want to put for x? I want to put x equal 1 because if it is lambda, then at x equal 1, function is not continuous. Therefore, I have to remember the very first class. The function is not continuous, then I have to put f1 plus f1 minus divided by 2. But here, luckily, at x equal half, function is continuous. Therefore, I can replace f half. So, minus pi by 2 and f half is 1 minus 1 over 2 square, that is 1 over 4. Therefore, I am getting this one. Therefore, I am getting minus infinity to plus infinity, this one. But if you look at the integration, they are asking is 0 to infinity. So how to convert my limit to 0 to infinity? Here I am originally having minus infinity to plus infinity. So now I want to think. But fortunately, if I look at this function, if I look at this one, this is an even function. Therefore, what can I do? I can break the limit to 0 to infinity so that I have to put 2 here. Then I can put 2 times 0 to infinity. Therefore, answer of that one will be minus 3 pi by 2 by 8 divided by 2. So I get minus 3 pi by 16. So that is the answer. Do you understand now? Hello, do you understand, students? Right. So I stop here now. Time is almost 4 o'clock. I will upload the video.